Hi students, Mr. Epperson here. This video is on intermolecular forces. In this video you'll learn what intermolecular forces are and what impact they have on molecules and their interactions. To demonstrate sort of the second learning goal, we're going to watch a quick video that shows water versus alcohol in an experiment that's called the penny drop test. Now in this test, the first chemical that they're testing is water. Their alcohol is going to look very similar in appearance, except you'll notice something certainly very different. So as he starts to drip the water, what we're doing is we're counting how many drops he's putting on there. And I've kind of sped the video up a little bit, but notice what happens right around now, basically, as he's adding more drops. It seems like the penny will basically not hold any more drops, but he can keep adding water. And maybe you've noticed this property to water before, that, wow, it can really beat up quite a bit before it overflows. Let's compare that with alcohol. In this case, the alcohol is called ethanol. This is food grade alcohol, and we'll see how many drops the penny holds. Okay, only 18 drops. Now, the difference in those is basically explained by two things. One, the idea of surface tension with different substances, but really, where does that come from? The second explanation is what's called intermolecular forces, and we can understand the different intermolecular forces that ethanol has versus water to see why one makes a bigger bubble and one can't hold as many drops. So what are intermolecular forces? Well, basically that first part of the word called the prefix, inter or intra, we're going to compare the two. Intermolecular means between molecules. Okay, so between molecules, and intra means within. So within the molecule. Well, what does that have to do with bonding? Well, an intermolecular force is a bond between the atoms. An intramolecular force, we've already learned about last semester, with covalent and ionic bonding. So intramolecular forces is already where we've been. Intermolecular forces is where we're going today, and it's just between two or more different molecules. Okay, so when two molecules get close, interactions occur, and those interactions are called intermolecular forces, and usually they are either attractive or repulsive. We're going to mainly learn about, the attractive property today. So there's a couple different ways of understanding intermolecular forces. Essentially, there's three types. I'm going to sort of detail them. You'll see in this kind of like darker brown color the first type. So these intermolecular forces are also called van der Waals forces. I'm not necessarily so picky that you remember that terminology, but just so that you are familiar with it if you see it again, van der Waals or intermolecular forces, those are the same thing. Well, the first intermolecular force is called London dispersion forces, and just to break that down, we'll do that in a moment after we go over the second term here. DipoleDipole forces is the second kind of intermolecular force. So let's talk a little bit about the difference between these two, and then I'll tell you the third category. The first category, called London dispersion forces, these are relatively weak forces. And where you're going to find them is every single molecule or atom will have the London dispersion forces acting on them. So that's the first kind, but it's very weak. I'll talk more about how it works in a moment. DipoleDipole forces, we've already talked about this a little bit in our lessons. These are strong forces, and we're going to talk about a subcategory here in a second called hydrogen bonding. But where do you find DipoleDipole forces? Well, essentially only in polar molecules, okay? So only in a polar molecule will you find this DipoleDipole forces, because it relies on a dipole, which is another word for a polar molecule, a relationship to a polar molecule. So how about that third category there? It's a subcategory of DipoleDipole. but it's so unique and important that we kind of use it as a category of its own. Hydrogen bonding only occurs in small polar molecules, including the elements F, O, and N, and it is the strongest intermolecular force, IMF. Okay, so IMF is a good abbreviation to know, IMF, and that is the strongest IMF. Okay, so the first force that we're going to study is the London dispersion force, and this is the weakest force. I've actually forgotten to put one very, very key element here, and I'll go ahead and put it in right now. This basically is only existing on nonpolar molecules. Okay, go ahead and add that in. But as nonpolar molecules go, this is what they've got to work with. Electrons in the bond of nonpolar molecules. Let's go ahead and draw the most simple nonpolar molecule there is, H2, okay, hydrogen gas. Those electrons in that bond, there's only two of them, right? Two electrons. They move between the two hydrogen atoms in sort of a circular pattern, just around them. And though they move in this sort of predictable pattern, you can kind of predict where they're going to be. It is somewhat random where they are. The reason for this is that electron sort of movement is very, very difficult to predict with any sense of accuracy in terms of physics. Knowing where the electron is not something that's easy to do. So we sort of just make a probability statement saying it's going to be somewhere around here, but the electron could kind of occur almost anywhere technically, but it's probably going to occur very, very often super close to the atoms themselves, because that's really where it wants to be. But it might from time to time escape some ways away and float around. In the same way, electrons not only can just occur in different places, but they can also occur on the same side. If there's two of them, they could technically be on the same side at the same time. They could, of course, be, on different sides. That's probably more often the way that it is. But in this relationship, with just two electrons and the single proton that's in the center of each atom, think about what's going to happen if, by chance, two electrons and those two electrons end up around the same atom at the same time. You're actually going to have a slightly negative charge on this side, and that'll leave this side exposed with a slightly positive charge. This is the idea of the London dispersion force. It's a temporary polar relationship that occurs, temporary dipole, that occurs when the electrons just randomly shift around. So the electrons are in the bond, moving randomly, but then sometimes they temporarily shift just to one side due to this random movement, and this causes this temporary dipole. As a molecule with a charge moves towards another molecule, that molecule doesn't even need to have a charge. It will actually have the electrons pulled towards it if it's coming in contact with the positive side, or pushed away from it if it comes in contact with the negative side. And so you have what's called an induced dipole, the induction of a dipole, where that negative charge kind of pushes away the negative electrons from the other atom, and you get a positive charge on this side, and a bond forms between those two. Now, this is a very weak bond, and it's sort of temporary, but things on the very small atomic and molecular scale can work at this speed and at this very, very minimal amount of time and work and effort in order to actually create some bonding force. And what's this force going to do? Well, it can cause physical properties like you saw with the surface tension of a substance. It also is responsible for keeping things in the liquid state versus the gas state, or even a solid state versus a liquid state. So the more force that something has kind of binding it together, the harder it is that its molecules are going to slip apart and move around. So that's basically what we're trying to see with these intermolecular forces, is how do those apply to those molecules, and what is it going to mean about the state that they're in, the state of matter that they're in, or any of the other properties that we're interested in. Eventually, the disappearance of this temporary dipole causes the electrons to shift back into their original position, and the bond is lost, right? But then another bond forms somewhere else. So it's sort of a random and rapidly shifting process. one thing that's kind of interesting about London dispersion forces, is that the larger molecules actually have a greater London dispersion force strength. And the reason for this is because larger molecules, like these ones on the side, have more electrons to play with. And there's kind of more, they kind of flow around a little better than if there's just a few of them. And so the larger something is, the easier it is for these electrons to move around. And if you do get that charge build up on one side and, it's slightly negative, then you'll have a slightly positive side on this end. And the difference between those two temporary dipoles can be a little larger. And the result of that, if you notice the numbers here, is that the larger a molecule gets, the higher the boiling point. That means it's harder to boil that substance because there's more bonds holding that thing together. So that's just one example of how these intermolecular forces affect physical properties, like boiling point. So that's the first force. The first force called London dispersion. The second one is called DipoleDipole forces. Okay, this only occurs in a polar molecule, only in polar molecules, and it only happens when the polar molecules align themselves in direction of their dipoles. Right? If you remember the way the dipole works, you've got negatives and positives, and we sort of show that by putting the little symbol here, delta, and they get arranged in negatives and positives, sort of aligned together. So that's how a dipole-dipole bond will occur between the actual permanent dipole that exists within an element, which of course happened because there's different electronegativities between those two atoms. So they align themselves so that their oppositely charged regions of the neighboring molecules are near each other. And when that happens, that means that there's a bond literally between those two. It may not last forever. Eventually that atom and molecule might break off and go somewhere else. But if there's enough stickiness keeping those two molecules together, it's going to be harder for you to boil that substance, or if it's got a surface tension, other different forces that are interesting, other different properties that are interesting based on that force. So another interesting thing about this is that it's kind of like an ionic bond, but it works with partial charges, right? Partial positive with partial negative. It's kind of like sodium and chloride, which is Na and Cl with a minus and a plus. So it's kind of the same idea, right? With the partial negative and positive sticking together. This concept isn't that hard. You just have to identify which is going to be positive, which is negative, and noticing that there is a permanent dipole there, it's going to have a dipole-dipole force effect. Now onto the biggest one, the most strength in terms of intermolecular forces, and it's a dipole-dipole force called hydrogen bonding. This only happens in polar molecules that contain N, O, and F. So if you notice, this is water, right? This is not water, this is ammonia, NH3, but water, of course, is H2O. As long as you have a molecule that has hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluoride, which is HF. This is an acid called hydrofluoric acid. You will have a hydrogen bond formed between the electronegative atom and the hydrogen atom. So between the electronegative atom and the hydrogen atom, I had them backwards there. There's a bond that will form between those. And think about why this is. It's because hydrogen is positive and the electronegative atom is negative. But it's like an extreme difference. And here's why. Because if you remember, hydrogen is a proton, one proton. Hydrogen's got the number 1 and a single electron, right? If it's got just one electron, when that electron gets pulled over to a big hungry oxygen or nitrogen or fluorine, a very, very electronegative atom, when it gets pulled over to that one due to the high electronegativity, remember it's still shared in the bond, but it'll get pulled over more often towards the oxygen. It's basically now just totally naked. And though, of course, the electron can come back, and, it does come back, and it's part of the bond, that single proton is basically kind of out there on its own and pretty exposed. And that very, very positive charge is almost like a whole charge, but it's still, we still call it partial positive, not just a +1. It's going to be still partial, not quite a whole charge. So, but you get the idea. It's a very, very positive charge compared to just, some other atom that has just a slight dipole or something on it. It's a very, very strong dipole. So the effect of that, in addition to usually these being pretty small molecules that can kind of fit together very closely, substances that have hydrogen bonding get a lot of really interesting properties, and actually occur in a lot of biological molecules too. Something like DNA, and proteins, those tend to have hydrogens all surrounding them, and a lot of nitrogen and oxygen in them as well. And so you'll tend to get a number of hydrogen bonds formed between lots of different biological molecules, and it helps keep things together within our own body. For instance, 2 DNA strands are connected via hydrogen bonding. One big long molecule of, the one strand of DNA and the other molecule of DNA is sort of stuck together in the middle at the zipper, and those two parts that are stuck together are held together by hydrogen bonds. So that's one way of understanding the impact of intermolecular forces and how the 3 different types work, and I hope that was helpful.